as a proportion of population. That's where the US is really bad.
Okay, welcome back everybody. So I was saying that the Jacobian can be computed. It's gonna be a long calculation, and I'm not sure if I'm gonna give you the details, but it's you have to use this line. Oh, sorry. You have to use this line here. you have to use this line here because there's a 0 here, right? So it's much easier to compute the determinant using this line here. So it's cos pi, right, times the determinant of these two here, which will be minus rho sine phi sine theta, right, times rho cos pi sine theta minus rho squared cos phi sine phi. Well, let me write it on the new line. Minus rho squared cos phi cos theta squared of theta sine phi, right? Now there will be a 0, and now there will be now minus rho sine phi rho sine phi square, right? So we are developing the determinant from this point of from this along this line here. So if you look carefully, that's exactly what I'm doing. Rho squared sine phi squared cos theta squared plus rho sine square of phi sine theta square. Now the thing is, there will be a lot of thetas and phi's, and there will be a lot of cancellations. So if you look carefully, you will get that this is equal to minus rho squared cos square of phi sine phi sine theta square minus rho squared cos phi squared sine phi times cos square of theta. Okay? So the reason is there will be a lot of cancellations. For example, which one? For example, this one with this one. Okay? And then what? Sine phi. Yeah. And then this one with this one. Is it clear? So this is sine theta squared, and this is the same thing here, right? So it cos theta squared of sine theta squared is gonna give you this one, and then here, here the same thing happens, and it'll give you this. And then again, there will be a lot of there will be another cancellation, which is this one with this one, because it's same number here, which is minus rho sine. Oh, sorry. Minus rho am I doing the right thing here? Let me see. Yeah, you just have to be careful. Mm-hmm. Mm-hmm. Yeah. It's cos phi. Yeah. In any way, that's the result. You just have to look at it carefully. You just make sure you understand it. But that's the result. It'll give you this, right? And this one again, you have a cancellations because you will add this one with this one, and then you will get exactly cos squared plus sine square of phi, right? Which will be minus rho sine phi, right? I mean, just do it. I mean, there is nothing hard in that. I mean, it's just keep be careful that you will have to use basically just the formula sine square plus cos square 2 times. 1 time to simplify this one and 1 time to simplify this one. And here are the details. You can just look at it carefully when if you're really interested. But the point is not, the point is this. The point is the Jacobian now, the Jacobian is now given by rho square sine phi. So magically, right? Right? Because the absolute value is not sine phi always. It's because sine phi can be negative, but because phi is between 0 and pi over 2, right? So magically, we get the exact factor we get when you go from dx. You remember when you go from rectangular coordinates to spherical, you have to be careful to not forget about rho square sine phi. So you get it actually here in the Jacobian. So the integral over the region R of the function f x y z dv is the integral from 0 to 1, from 0 to pi over 2, from 0 to pi, of whatever the function you have, but you just have to be careful to substitute rho sine phi cos theta, rho sine phi sine theta, and rho cos phi, and then you have to add the Jacobian, which is rho squared sine phi, and then you integrate over the region, which will be d rho d phi d theta. Which is exactly the formula we got when we go from rectangular to spherical. Okay. 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 So with this, we are done with the 3 variable integration. So that's all what you need to know. So the exercises in the problem set, I would recommend that do not try the interesting one, because you need to do a lot of them before, because you need try to do some mechanical one before, right? And also get some exercises from the book, right? You have the solution manual, so go there and do some of them, and then you can try the mechanical one, and then you can try the interesting one, because the interesting one, there are some of them that you will need a bit of acquaintance with tree integration. So the way you do it is you do some easy ones from the book, and then from I've included some in the mechanical ones, but the one in the interesting ones, they're a bit harder. Okay, so that's what we'll need to know about the integration in 3D. All right, so now we're gonna jump to the last section of the course, which will be dealing with vector fields again. So we will do the analog of curl of line integrals in 3D. That will be a surface integration. So we want to do this, right? So remember what we did. We had curves and we had vector fields on the curves, right? Vector fields. And we did the line integral over the, right? We call the integral of ds, right? The integral of some, right? So some vector field f dr. Remember that over a curve or a function f ds over a curve or something like that. So we're gonna do this for 3D. So what is the analog of a curve? In 3D, it's a surface. So the first, all of that will start with vector fields in 3D. Okay, so as you're gonna see, it will be more or less the same thing as in 2D. There's nothing new. There's nothing new. It's just gonna be in 3D. So a vector field in 3D is a vector valued function okay? Defined on a subset E. Okay? One example, the gravitational field. Gravitational force field. So what is this? I'm gonna change the notations here. Okay, let me change the notations here. It's F evaluated at the point X. This is the point X. So sometimes you're gonna see X, sometimes you're gonna see X, Y, Z. So Fx is given by minus M, capital M, G, norm of X, Q, X. But that was in the assignment at some point, right? So if you have I don't know, the mass of the sun, and then you have the planet Earth, right? Then you will have a force that goes along the direction MM, but directed toward the sun, right? But be careful, this is not a two-dimensional. This is not a two-dimensional vector field. It's also, if you have something here, also along this line here. See, but it's always directed. Okay. Where X is square root of X squared plus Y squared plus Z squared. Now make sure you understand this example, because this is the example I'm gonna use for all the subsequent concepts I will be introducing. So in components, this vector field is given by minus M, capital M, G, X, right? Because what is X? X is X, Y, Z. Divided by X squared plus Y squared plus Z squared to the power 3/2 I plus minus M, capital M, G, Y. I'm sorry, this is okay. Minus M, capital M, G, Y, X squared plus Y squared plus Z squared Z, to the power 3/2 G, J plus minus M, G, Z over X squared plus Y squared plus Z squared to the power 3/2 K. Okay, so that's exactly this expression, but expressed in terms of x, y, and z, and more explicit. So these are the function p, q, and r. Okay. Okay, you remember the gradient of the field? We'll have the same concept here, which is the gradient is, the gradient of field, we can define vector field using functions of free variables. Okay? Is a two variables functions. Okay, so here again, here's the example, the same example as I did. So if you take the function, on R3 without the point 0, 0, 0, then take the function on R3 f x, y, z equal to minus m double m g over square root of x squared plus y squared plus z squared. Then the gradient is equal to f, which is the gravitational field. That's the example. I mean, if you do the calculation, you will get exactly the gravitational field here. Take the gradient, and you will realize the same thing. Okay. Okay. Now, line integrals. In space. We did line integrals in 2D. Remember, we had a curve in 2D and we did the line integrals. Well, the exact same thing, we can do the exact same thing in 3D. So a curve C in 3D, right? Smooth curve is given is given by parametric equations x is a function of t, y is a function of t, and z is a function of t, okay? T between A and B. If x and y and z is a function that is continuous of some region containing C, to define a line integral of f along C as the limit of f xi star yi star zi star delta se, okay? Let me just be more explicit here. If you have a function, right? If you have a line, okay? If you have a line, okay, you take delta, SE, okay? And you take a point that is here, which is xi star, yi star, zi star, okay? And then you divide this curve into 3D, into a lot of small curves, and you just take the limit as this very small parts of the curve will go to 0, right? And when this function is continuous, this limit always exists. Okay. So, and the way we solve this limit is, you can go back to the 2D case, but you have to approximate the curve by lines, and then you have to use the tangent line. All of that, it's not that hard, right? Because delta x or delta x over delta t is same thing as x prime when t is very small. So when you take t very small, delta s will be very small. So delta t, right? They did the exact same thing. So as for the 2D case, we get the limit when n goes to infinity of the sum. This is by definition will be the integral of the curve, the function f(y) z ds. Okay. And as I said, you can approximate this delta s using Pythagoras theorem, which will be the integral from a to b of the function. But now, function is defined everywhere, but when you are on the curve, you have to evaluate the functions on the curve. Okay? Times square root of x prime t squared plus y prime square t plus z prime t squared dt. Okay? You can also write this integral as integral from a to b of the function f, but evaluated at the point rt times the norm of the vector r prime dt, right? Because the vector r is the one that gives you the line, right? So the vector r, right? So that's the vector r. Is the one that's gonna follow the curve, right? Okay. 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 We can also, by the way, I'm gonna scan my lectures notes, so you can go there. It's much more readable there. We can also define line integrals along C with respect to x, y, and z. See, remember those dx? You can do the same thing. For example, integral function fx yz dx, right? Now instead of delta s, we're not going to take delta s. We're going to take for if this is delta s. So when you move some very when you move along the curve for some small t, you'll get a delta x here. So we're going to multiply by this delta x, not the one here. Right? Then you can do a same calculation to evaluate this limit. So this are, yeah, can you scroll to the previous page? Yeah, sure. This one? Okay. So again, these are the exact same concepts. There is nothing new. It's just in 3D instead of 2D. So is that okay? You're fine? Or the one who wanted me to scroll up? Okay. So here's an example. Evaluate L where F Okay. So this is mechanical. So what is our prime? Our prime is 3 t squared I plus 2t j. And what is f? But evaluated at the point RT. So you just take t and you plug in. So it's t cubed times t squared I minus t cubed square j. So I'm going back and forth from this notation here to this notation with I and j. T to the power 7 I minus t to the power 6 j. So L, see, because basically I prime is when you take the scalar product, okay? So this is also, so the most challenging maybe would be here, it would be the notation, right? You don't know what is what, right? Because here, but here is gonna be here is gonna be dx, and here is gonna be dy. So L will be t to the power 7 times 3 squared, right? Integral from 0 to 1 dt plus the integral from 0 to 1 of minus t6 times 2t. Okay. Okay. Line integrals of vector fields. Okay. Uh, okay, so let me take a break again here for 10 minutes and then we'll be back. Unfortunately, we're moving a bit slowly today. So my goal is to finish, hopefully, just to introduce curl and divergence. And yeah. Okay, so I'll be back at 12:15. Hi everyone, welcome back. So let's do line integrals over vector fields. So if f is some vector field that is continuous, then the work done by f along a curve C from R of A to R of B is defined as the line integral of the curve of the product, the scalar product of the field x, y, z times t, right? So this is a scalar function, and then you multiply by ds, so it makes sense. And this is abbreviated as ft ds, okay? Okay, where C is given by RT of xt I plus y t of j plus zt of k, and t is the vector p RT divided by R prime t, right? I'm sorry about that. I don't know who's fixing it right now. Okay, and here the curve here is RA, RB. Okay. Hence, so the work Okay, so this is ds. And this is x t as in the curve. Okay. Okay. Find the work done by the field f x y z okay along the segment from 0, 0, 1 to 2, 1, 0. Okay. So if you have a point and then you have another point, how do you parameterize the curve? Is RT, okay? So here is the point 0, 0, 1, and here is the point 2, 1, 0. So it's the vector that gives you the direction of the curve, of the line, which will be the point 2, 1, 0, minus 0, 0, 1, t, right? And then you start from any point on the line, plus 0, 0, 1. Okay, so if you do the calculation here, it will give you 2t, t, minus 1 minus t, and t is between 0 and 1. Okay? So the work is given by the integral from 0 to 1. Now you have to take this RT, plug it into the equation here, fxyz. Then you take the scalar product with R prime, right? Right? Here maybe it's better if I just and R prime So let me switch again to the notation of, just to make you a bit familiar with every kind of notations we're using. So it's 2, 1, minus 1, which is 2i plus I plus j minus k. Okay, so just take the derivative of each component and it'll give you this. So the work is the integral from 0 to 1, and that's gonna be a long thing. 2t minus t squared I plus t minus 1 minus t squared j plus 1 minus t minus 2t squared, the whole thing, k, right? And then this is scalar product with the factor 2i plus j minus k. Okay? So, because we are running out of time, I will let you do the competition here, but it's really long. Just be careful when you do this kind of competitions in the quizzes or anything else. I mean, it's normal that you do, it's like, it's normal because these are like very long competition. It's normal. I mean, I do mistakes, so so it's normal. But just try to focus and go slowly. No, it happened to us sometimes. Minus 1 plus 2t minus t squared minus 1 plus t plus 4 t squared. So this is a polynomial. There is nothing hard in that, in integrating this thing, and you just have to do it. And it's supposed to give you 7/3. Okay? So here we have also the fundamental theorem of line integral. So if you have a curve from RA to RB, right? We get, okay, if F is a three-variable function, then the integral of the gradient of the function times dr on the curve will be equal to the integral from A to B of the gradient of F, the value R prime T dt, okay? And this will be equal to, by definition of the gradient, so it's B F B X times B X dt plus B F dy dy dt. See, I'm just writing this and taking the scalar product. plus df dv dv dt dt. And now recall what we have learned in the first half of this class. This is just intrinsic variable, the derivation in chain. This is not the derivation of the function f. Function f evaluated at the point xt, yt, dt, dt. And this is the function f evaluated x of b, y of b, z of b, minus f of xa, y of a, z of a. Okay? Same thing as writing f, evaluated at the point rb minus f, evaluated at the point rb. So it doesn't depend on, as we were saying for 2D, it doesn't depend on the curve, right? It doesn't depend on the curve, and because it's a gradient of a vector. Okay, so, and then, yeah, that's basically it. Sometimes you if it's from the gradient, if it comes from, if a vector field comes from if it comes from the gradient of the function, then it doesn't depend on the curve, right? And here I have an example, and it's quite clear how it is done. So if we choose to include it in the assignment, maybe you want to take a look. But in the next example, which I'm not going to introduce here, well, they'll give you a vector field and they'll tell you find a function such that the gradient of this function is the vector field. That's exactly what we did in 2D, but you just have to solve a system of equations. But take a look on the notes. Okay. Okay. Okay, so now curl of a vector field. So here are some new concepts that are purely, you know, we could have introduced those things in 2D, but it won't be that much interesting. So the curl of a vector field is a new thing. There's like the real new thing that appears in 3D. So let f. So as you're gonna see, it's a lot of computations. Curl and divergence, a lot of computations. Let f plus q j plus r k be a vector field. On R3. Okay, suppose that all partial derivatives exist. Then we define the curl f of a vector field is the partial derivative of r with respect to y minus partial derivative of q with respect to z I plus. Let me do it on the next slide. Plus del p del z minus del r del x j plus del q del x minus del p del y. Okay. So now you might ask yourself, how can I remember this formula, right? So formally, let's check something. Okay, so yeah, so there will be a lot of formal computations here. Formally, this is given as the determinant of I, J, K, del X, del Y, del Z, P, Q, R. So here's the thing. This is not a number. What we have here is not a number. This is not a vector. It's not a vector. It's a formal vector. This is an operator. It acts on something. So, but when you do the formal computations of a determinant, it gives you exactly this. Say, for example, you take I, and then you take b del y of r minus del z of q, give you this. Right, del z of q. Now we take minus, right? Take minus, but then you take dx dr dz dp, but it's minus, so it gives you this. Okay? And this is the notations we use. We use the notation as we take the formal cross product of the gradient vector with f. So we use the notation, the curl of f okay. So this is an example just to make you comfortable with this calculation. Find the curl of f where f okay. So the curl of f. Okay. So if you take the partial derivatives of all of these functions, it's 0 plus 0 plus 0. Okay? Okay. So it turns out that the curl of a gradient field is always 0. In fact, let f be a function on R3 with continuous second order partial derivatives. Then the curl of the gradient is the cross product of the gradient times the gradient, which is the determinant of I, J, K, del X, del Y, del Z. Here we have del X, F, del Y, F, del Z, F. Okay, so this is why we say that it has to be continuous second derivatives, because by Clairaut. Remember the theorems, the theorem in first half that says that these are always a 0 if the second derivative is 0. Is the second partial derivatives are continuous, they're always 0, which will be the case in practically in all the real situations. Okay. So you might ask, okay, what kind of interesting questions we can ask? So be aware, this might appear that all of these are just computations, but here's an example where we already gonna mix. We're already gonna mix everything that you know in a question, and you have to use all the tools that you have been introduced to. So for example, here's a question that requires a little bit of thinking and using what you have just learned right now. So for example, show that the vector field F is given by x, y plus y, j plus z, y, k is not conservative. See? So here, remember what is conservative. Conservative means that it comes from the gradient, right? It comes from the gradient of a function. So what we can do is you can uh, see, for example, if it's conservative, then it's the gradient of some function, and the second derivatives are continuous because anyway you just have to. The first derivatives are given here and are polynomial, so we can apply this calculation here. So compute the kernel. Okay, which is not zero. So f cannot be conservative because otherwise we would have kernel of f is zero. Again, because the first derivatives are already given, suppose you have that it's conservative, so it comes from the gradient. So you have the first derivative, which are the x, y, z. So the second derivatives are continuous because they are just functions of what, like in 1, 0, 1, z, or y. So they are continuous. So if this is true, then we would have that the kernel is v0, but the kernel is not 0. Okay, so here is another theorem. We have so here we ask the question, show that it is not conservative. Now, how can I show that it is conservative? We have the following theorem. To verify vector field is conservative. F is a vector field defined on a simply connected region, right, with component I'm gonna say in a moment what is the simply connected in single words. Component with component functions having, I don't know if this is the best way to say it, having continuous partial derivative and if you compute the curl and it gives you 0, then F is a conservative vector field. Now, I would like to ask you, just try to remember the test that we had when we were in the 2D case. You remember the test, you have to take dx dy of q minus dy dx, dx of q minus dy of p, you know, remember that? So this is the analog of that. But the region has to be simply connected if you want it to be, you know, if you want it to work. And simply connected, you can just take the definition I gave you in the 2D. It means that there is no hole. For example, if you have a ball and then you just remove this. So this is not going to be simply connected because, again, there's a hole, right? So, yeah. See? So if this is the region R, this is the region D in your, this is the region where the vector field is defined, and then you just remove this ball. So it's really defined on a kind of between this little sphere and right, and the larger sphere. So you're not gonna be simply connected because there's this hole here. There's this hole here. So this is not gonna be simply connected. But in the practical cases, we'll give you a vector field defined on R3. So it'll be simply connected. So you just have to check if the curl is 0 or not, right? And you will see why. And this has to do, remember, this has to do with the bound, because remember how we did prove it. We proved this using Green's theorem. And there is the analog of Green's theorem in 3D, which is Stokes' theorem. And it has to do with the boundaries, right? If you want to prove this theorem, you will have to deal with the boundaries, because then you're going to go from an integral of a surface to an integral of the volume to an integral of surface, and then you have to go to the boundaries. And then when there is a hole, there will be a problem with what is the boundary, right? If there is no hole, the boundary is clear. It's just what you can see, right? But when there is a hole, there is a problem of the boundary, and you cannot really apply. So, yeah. So this is a theorem that we're gonna prove, but not now. We're gonna prove it using Stokes' theorem. Yeah, so let's apply this one to the gravitational field. And this is a very interesting calculation because the gravitational field is a very complicated field, but Yeah. Now I'm thinking about something. Is it the best time to introduce this one here? Uh, okay, but I don't wanna. Yeah. Okay. Yeah. So basically, the gravitational field, why I wanted to introduce it is because it is not defined at the origin. So you really cannot define, it's not defined on R3. So you can only apply it. It'll take a bit more, you'll be a bit, you'll need to be a bit more subtle with the gravitational field because it's not defined at 0, 0. So remember, what is the gravitational field? This is the example I want to, so, but the thing is, you cannot apply the gravitational field just like that. You need to apply it where it makes sense. For example, consider the gravitational field. Oh, so let me just write what I want to do, and then we'll continue next time. So I will just apply the example to the following field. X over xy, y squared, z squared, but define over it's already 1 o'clock, but let me stop here and I'll continue next time. But just try to read my notes, and there will be, I guess there will be a makeup class because we didn't have a class yesterday. I was thinking maybe we had, but we didn't. So I will just check with the department how we can manage that. And because we're running out of time, and we would like to finish the material so that you can be ready for assignment 4. So make sure you read your emails because you're gonna hear from me when and how you can join the makeup class if there will be any. All right. So have a nice day, everyone, and sorry for the quality of today. It wasn't the best, and I hope I can see you next week. Good luck.